Can everyone hear me? Okay. Okay. Hi, everyone. Let's get started. So we have been talking about neural nets for the past couple of sessions. In particular, in the previous session, we started by talking about some of the practical issues that arise when working with neural networks and when trying to train them. We talked about a few strategies to make sure that stochastic gradient descent doesn't get stuck in bad local minima when we are trying to use it to train a neural network. We talked about how to set the learning rate, what kind of a schedule to use. We also talked about learning with momentum. And then we talked a little bit about the landscape of all local minima when you're trying to train a neural network. And we thought about how there are different sources of symmetries, and as a result, we have many different local minima and local global minima potentially that all of them represent the same function, but they basically in the landscape of the optimization landscape, they are different points. So another issue that we discussed extensively was the possibility of overfitting in neural networks. So remember that neural networks usually have a lot of parameters, and as a result, the possibility of overfitting is very high. So there were multiple ways to avoid overfitting. One was regularization, adding a term to your optimization objective that makes sure the magnitude of the weights are not too big. But we saw that that is not very practical due to the fact that training neural networks even once is pretty expensive computationally, so you don't want to do it multiple times. And generally, when working with neural networks, we already have a lot of parameters, so unless we really have to, we shouldn't introduce new parameters. So another approach we talked about was early stopping, and the idea there was that we didn't want to let stochastic gradient descent to converge, because then that would be a recipe for overfitting. Why is that? Because due to the universal approximation theorem, we know that with sufficiently many hidden units, you can basically represent any continuous function. And if you allow the stochastic gradient descent to converge, it's very likely that you're going to fit the noise. That is why you don't want to allow it to converge. Instead, you want to stop the stochastic gradient descent when you see that the accuracy on a separate validation set is starting to go down, right? So that's when you want to stop stochastic gradient descent. And the other regularization approach we talked about, which was a recent one, was dropout regularization, in which we, in each round, we dropped some of the hidden layers uniformly at random with some probability p, and then we did the back propagation, forward propagation, assuming that those do not exist in the network. And the idea there was that we wanted to make sure that we don't rely too heavily on any single hidden unit in making our prediction. So that was those were some of the important tricks and strategies that you need to know when working with and training neural nets. And then towards the end of the previous session, we talked about the fact that we, in many settings, given the knowledge that we have about the input data, the training data, there are usually a bunch of transformations that we ideally would like to be robust against. For instance, when we are working with handwritten digits, ideally we would like our predictive model to be robust against shifting the handwritten digit around, rotating it, scaling it, and that kind of thing. So we would like to get the same prediction no matter if we apply any of these transformations. So again, there were a bunch of different approaches to make sure that we have this invariance property. The last one that has been applied very successfully and widely, especially to image recognition, was convolutional neural nets. So remember that convolutional neural networks, or CNNs, are a particular type of neural networks, and at a high level, what they do is that they reduce the number of parameters in your model. So far, the type of neural networks that we've talked about have been fully connected. We've basically only talked about fully connected layers, right? So my input is fully connected to the next hidden layer, and so on and so forth. So with convolutional neural nets, what we do is we do weight sharing. And the idea there was that by you could think of them as applying some kind of filter to the image, trying to extract information from image patches. So we started with giving you a high-level idea of what this convolutional neural net architecture looks like. We have the input layer as usual. We have a convolution layer, which basically does the filtering that we just talked about. We have a pooling layer that I'm going to talk about in a few minutes. Then, after having a bunch of these convolution pooling layers, you might want to have several fully connected layers, and then the output layer. So this is a very simplified view of convolutional neural network architecture. Okay, so remember how the filtering worked. We went over a couple of examples. The way it worked was that we had a filter with the same depth as the image representation, the input image representation. And what you did was you would slide this filter over the image, right? And then get a potentially more condensed representation of the image. Not necessarily always more condensed, but without padding, we usually get a smaller representation of the image. And the idea is that these filters are supposed to extract certain information. They are supposed to be specialized to extracting certain information from image patches. For instance, one filter could try to detect edges in the image, one filter could try to detect colors, and so on and so forth, right? So this was the idea. And then remember that these filters, compared to having like a fully connected layer, having these filters basically means that you're doing parameter sharing and you're applying the same parameters to every image patch. And that drastically reduces the number of parameters in your model. And as a result, you can have a deeper network because you have less parameters and you can still train them. And let's see. So this was the high-level idea with working with convolutional neural nets. Some terminology that you need to know. Filter is the matrix that you multiply. You don't matrix multiply. Just I want to be very clear about that. So this operation is called convolution, and all that is that you do you compute the dot product of the filter with the image patch, right? So this was one example. So you had a 3x3x3 filter. You applied it to an image, a padded image. The zeros were the padding part. You did the inner product, and then you would get this green representation over here, right? Actually, I need to turn on my pen. All right, so, and then lastly, we talked about how one can compute the dimensions of the resulting output when you apply a filter to an image, right? So there was this formula that, if you think about it, is very easy to understand why. So, we went through the previous example and saw that the dimensions of the representation is exactly 3x3. And so that was when we concluded the previous session. So what we are going to do today is we are going to talk about pooling. So remember that another important operation in the convolutional neural networks are the pooling layer. And pooling is basically pooling is implementing a very simple idea. So the goal is that you basically want to make sure that you decrease the number of trainable parameters, and you wanna make sure that the image representation that you have doesn't get too big. You basically what you do with pooling is that you apply it to the current representation, you get a smaller representation. And how does it work? So there are two pretty commonly used types of pooling. One is max pooling and the other one is average pooling. We're going to only talk about max pooling, but the average pooling is pretty similar. So what you do is that you let's actually look at an example of how this works. So suppose this is the representation that we currently have of the image. We've applied a bunch of filters, and this is the representation we've currently derived. What max pooling does is that it basically subsamples this. And in particular, in this particular example, what it does is that it breaks down the image into 4 2x2 submatrices, right? And then in each of these matrices, it takes the maximum response. So remember, what each entry of this matrix is representing is the application of the filter to a certain patch of the image. And these are patches that are nearby, sorry. So these entries correspond to nearby patches. So basically, what max pooling does is that it goes ahead and compute the maximum among 1, 1, 5, and 6, which is 6. Whoops. The maximum of between these 4 numbers, which is 8. The maximum between these 3 and 4, right? So the idea is very simple. Again, you can have different strides. Remember, stride was the length of the step you would take every time you wanted to move the filter, right? So the same idea here. You could have different strides. But the general idea is that you would get a more condensed representation. So let's think about a more real-world example for a second, and to get a better understanding of what this pooling does. So, for instance, suppose you have a filter that is trying to detect faces, right? So your filter goes over different image patches. It computes a response, right? And the higher this response is, the more likely it is that there is a face in that image patch, right? So all that max pooling is doing is that it says, look, I don't really care in which part of this nearby patches you found a face. As long as you found a face, I wanna keep that information, right? So I looked at a bunch of nearby patches. This one was the most likely to contain a face, so I'm gonna just keep that information. So that is the high-level idea behind pooling. So this was max pooling. It's easy to imagine how average pooling works. Okay. So let's move on. So there is this nice convolutional neural network demo. So again, let me quickly summarize. So the most important concepts you need to know about convolutional neural nets are the convolution step itself. So you might have a convolution layer, right? After convolution, you might apply a pooling layer. This is also often done to make sure that you get condensed representations and you don't blow up the number of trainable parameters. Right, so this is the high-level summary of what CNNs do. So there is this nice demo online that you can play around with. Let's see. So this is basically a demo that trains a convolutional neural net on the MNIST digit data set. So the network takes the input images are 28 by 28, and their depth is 1. So what you can do is that you can play around with different parameters. You can set the learning rate, right? So this is the step size in the gradient descent. Let's set that, I don't know, to 0.05. The momentum, let's set that to 0.1. Patch size and weight decay, right? So these are parameters of the parameters that you can set for training a neural net, and then after you do this, you can basically allow the training to unfold. Okay, yeah. Here, and this graph on the right-hand side shows the loss. And if we wait for a little bit, hopefully the loss that we are going to get is going to go basically to zero. We are going to get 0.99 accuracy or something. And I ask you to repeat this with a bunch of different parameters. So as you change the parameters, the speed with which you are going to get convergence to this 0.99 is going to change, but consistently, basically, you are going to get there, right? So as you can see, we've already are below 0.5. And the other interesting thing about this demo is that it has a nice visualization. In particular, it shows you the activations, and it shows the example prediction on a test set. So if you run your current trained model on this image, with high confidence, the algorithm is going to predict 1. So this one, the algorithm makes a mistake. It's a 7, but the model thinks that it's a 2. So as the training unfolds, these bar plots are going to change. And towards the end, almost all of them, all you're going to see is green, right? Meaning that you're very accurate. So this is a demo that's online, and you can use it. Back to the lecture. So, okay, so I'm going to talk a little bit about this paper by Zeiler and Farragus on convolutional neural nets, and just to give you a flavor of the type of research that has been done and how people usually study convolutional neural nets. And then we are going to try to get a better visual understanding of what happens inside these filters. So this diagram here is taken from the paper, and it represents a convolutional neural net architecture with a bit more detail than the one that we saw. So you have an image, you have a filter of size 7 by 7, that you apply to the image with the stride 2. This is your input image, and then you're going to get this new representation, right? Then with this representation, to this representation, you apply a 3 by 3 max pooling operation. You're going to get another representation, again, another filter, another representation, and so on, right? So yeah, you might have many convolution and pooling layers, and which make up a deep structure. And then you will have a bunch of fully connected units. And then once you have computed the confidence for each of your potential classes, which is 10 in this particular example, you're going to apply a softmax and make a prediction. So this is basically how people represent neural nets. Okay, so next we are going to talk about when you train a convolutional neural nets, what are the informations that these filters will be trained to pick up. So this is, again, from the Zeiler and Farragus paper. The illustration are from this paper. So on the top, you see 9 different filters in the first layer of the particular convolution neural networks that they trained on their data, on their image recognition data set. So this first filter, basically the one in the corner, looks like it responds maximally to diagonal lines, right? Same for this one with a different direction. Same for this one. This one over here is basically going to tell you if there is a lot of green in the picture, and so on and so forth. So on the top, you have the filter. You have a visualization of the filter. So again, remember that the filters themselves are matrices, right? And you can visualize them the same way that you would visualize an image. So remember, an image had a matrix representation, right? So now if you're given a matrix, you can also visualize it as an image. So this is what's happening in this top layer. And in the bottom, in these first picture. So this picture on the bottom shows you the kind of patterns that each of these filters maximally activate. And what do I mean by that? So if you apply, let's say, take this filter in the corner, right? So if you apply this to images like this, you are going to get a maximal response. This filter basically gets activated if you have an image like this. And as you can see, all of them contain diagonal lines, right? Which is what we expect this filter to detect. Similarly, for this green one over here, these are the type of images that maximally respond to the filter. So if you apply this filter to any of these images, you are going to get a big response. You are going to maximally activate the filter or the kernel. So this was a visualization of the filters in the first layer of the convolutional neural nets that these guys trained. And then if you move on to the second layer, these are the type of filters that when you train the convolutional neural nets, you're going to get in the second layer. So as you can see here, for instance, this one detects circular patterns, right? And this is the type of image that maximally responds to that to these filters. Similarly, this one seems to be picking up a certain texture, right? And these are the type of images that activate the filter. Or this one picks up yellow. I don't know what else. So you get the general idea, right? So this is what happens in the second layer. And as you move deeper and deeper into your convolutional neural nets, you can see that the kind of patterns that the filters detect become more and more complicated, right? So for instance, this one over here seems to be detecting people's faces, right? Or this one here picks up certain geometrical patterns. This one over here picks up text and that kind of thing. So the high-level message, the high-level idea that I would like you to get from these visualizations is that as you go deeper in the network, initial layers in the convolutional neural nets usually extract generic information about the image patch. Whereas as you go deeper and deeper into the convolutional neural nets, you're going to, the filters are going to be trained to pick up more complex patterns. For instance, this last one, layer 4 and 5, this one detects like bird eyes, or I don't know, this one detects dog faces, and so on and so forth. So that is the high-level message I would like you to get from this illustration. All right, so we are pretty much done with what you need to know about convolutional neural nets. What we are going to do next is that we are going to use Keras to implement a convolutional neural network. So Keras, among other frameworks, is a framework that allows you to very easily specify an architecture for your convolutional neural nets. It makes the whole process automatic. You don't really have to get into the low-level details. All you have to do is to specify your architecture, and it's going to take care of a lot of details for you. For instance, it is going to compute the derivatives for you. It is going to do forward propagation, backward propagation. All that is going to be done automatically. And what we are going to do next is we are going to basically just put together a very simple convolutional neural net architecture. You can also, use Keras to implement other kinds of neural nets, and as we will see, I'm going to also give you an example of that. And I guess with that, we are going to wrap up the CNN part. But let's first get into the tutorial. So I have to, because this is an older laptop, I have to switch between laptops. So bear with me for a couple seconds when I first switch between these. All right, so all I've done is that I've opened Python. So what you first need to do if you don't already have Keras installed is to add this library to your Python. So I'm going to assume that you have it installed, but if you don't, the installation is very easy using Anaconda. All you need to do is to do pip install Keras. And I'm not going to run this because I already have installed Keras. So just to give you a very high-level idea of how Keras works, Keras is a library for deep learning in Python, and it is very modular. You don't really have to, there are a lot of details that it takes care of for you. And in this tutorial, we are going to put together a very simple convolutional neural net and a artificial neural net using Keras. So the outline of what we are going to do is as follows. So we are going to first import the necessary libraries and modules, including Keras and so on. We are going to load MNIST. So MNIST already exists in the Keras library, so we can just load it from there. We are going to do some pre-processing on the data, depending on the backend. And then after we do the pre-processing on the training data to make sure that it is compatible with the convolutional neural net implementation in Keras, then we are going to define our architecture. After fully defining the architecture, we are going to compile it, let it train on it to get a model, and then we will evaluate the model on the test data. So a pretty standard procedure of training a model using training a model in machine learning. So let's get started with importing the necessary libraries and modules. So the first thing that we're going to need is to import NumPy, and the reason I need this is that I want the results to be reproducible, so I basically assign a specific seed, right? Then, whoops, what happened? I forgot the seed. Okay, then we import Keras itself. So from Keras, you import the sequential model type, which is basically just a stack of linear hidden layers. Then we also import the typical layers that we are going to use for convolutional neural nets. And again, this will include fully connected layers, dropout, flatten, and that kind of thing. We're going to talk about them in more detail shortly. So dense is basically the fully connected layer. Dropout will do the dropout regularization for us. Activation, we are going to specify what kind of activation function we would like to use. And flatten, I'm going to tell you more about it later, but the idea is that after you've done all your convolution and poolings and you wanna give the resulting output to the fully connected layer, you need to first flatten it. So you need to turn the matrix representation into a flat representation. So these are some of the frequently used layers when you're working with neural nets. And then we also need to import the convolution and pooling layers. So conv 2D and max pooling 2D. So the reason I'm using 2D is that the MNIST data has depth 1, so that's enough. So these are basically all the libraries and layers that we are going to need in this particular example. Now, what we are going to do next is that we are going to load the MNIST data from Keras library. There are a bunch of data sets available. We are going to stick with the one we have already talked about. And next, we are going to break this data into train and test, right? So oh, shoot, thanks. That would have probably caused a lot of trouble later on. Okay. Whoops, again, why? We're going to get there. Okay. All right, so let's make sure we've loaded the data sets correctly. So yeah. So basically in the train set, we are going to have 60,000 instances. Each one of them is a 28 by 28 image. You can basically repeat the same thing for test to see how many instances we have there. Okay, we have 10,000 tests. Now, because I'm going to use these. Actually, let's not define a separate parameter for them. So this was all we needed to do in order to load a data set from the Keras library. Next, we are going to do some pre-processing, and the reason we are going to do that pre-processing is that depending on the backend for this, which could be for Keras, which could be either TensorFlow or Tiano, for example, you might need to turn your images into particular shapes, right? So first, let's see what is the backend. What happened? Okay, so I think for Tiano, if I'm not mistaken, we need to first specify the depth. Otherwise, we need to put the depth last. So if the image data format is channels first. So again, remember that the depth of an image corresponds to different color channels, right? So if you have an RGB image, you're going to have an image of depth 3. In this particular case, we know that our images are of depth 1. So if we have this, then the input shape must be like this. Otherwise, the input shape must be like this. So this is not a big deal, really. All you need to do is you're making sure that your input data is compatible with, let's see. Yeah. What is it? Ah, okay. Okay, I'm not sure why I'm getting an error. What is it? That shouldn't be the issue. So again, you don't have to use command prompt, but okay. All right, so we're going to do a little bit more of pre-processing later on, but for now, let's start by massaging the labels, the class labels first. So if you look at the size of your white train, right? So what you see is that it basically doesn't give you the right representation. What you want is that for each instance, for each value of the feature vector, you want to know what class it belongs to. You don't want to get the class label. You want to have a kind of like a vector specifying whether it belongs to the first class, second class, and so on, right? And this is the first kind of representation. It basically, for each feature vector value, it gives you the class label itself. So we first need to turn these class labels into categorical variables instead of numerical. So there is a function that does that for us. The number of classes is 10. Huh. Okay, same for the test data. So now if you look at the shape, this is what you basically want, right? Okay, so we're pretty much done with the pre-processing of the data. Let's take a break a little bit earlier because I don't want to start defining the architecture and in the middle give you a break. So let's have a break now and we will restart in 15 minutes. Okay, so let's get started again. So I quickly finished the pre-processing of the data during the break. All I did was that I basically put them in the shape that I wanted. Remember that we have already decided what the input shape should be. I just reshaped both the test and the training data so that they have the shape that we desire. The other thing that I did was that I made sure that they are of type float, and also normalize everything so that they range between 0 and 1. Okay, so now we are ready to define a very simple convolutional neural net. So let's call that CNN. Remember that we have already imported this library sequential. So set the name also to CNN. Now what I want to do is that I would like to first specify the input layer, right? So all I need to do is I'm going to say to the CNN, add and the input shape must be the input shape that I specified before. The convolution layer I'm going to have 32 different filters in the first convolution layer, and I'm gonna let all of them be of size, I don't know, 2 by 2. And the activation is going to be, I don't know, rel U. Okay. So I'm going to have this one last. So the first argument is a convolution layer, next activation, and then the input shape. So one of these input shapes is the parameter of this add function. Sorry, I had a typo. So, okay. So we now have specified what the input shape should be. It should be 28, 28, and 1 with depth 1. We added a conv layer with 32 filters, all of them of size 2 by 2. Now you can basically keep going, add maybe more layers. Oh, by the way, actually, let's, before we add more layers, let's, so can you guys tell me what the output of this layer, what the size should be? Remember that we had this formula. I'm waiting for someone to compute it. So remember that the images of are 28 by 28. We are assuming the filters of are all of size 2 by 2. The stride is by default 1. So we have, and we didn't add any padding. So it's going to be 28, no padding, so we don't have to add the 2p. Then minus the size of the filter, 26, divided by the stride, which is 1, 26, and then plus 1, 27, right? So we expect to have 27 by 27, and the depth is going to be 32 because we have 32 kernels, right? Which is exactly what we get. Okay, so now let's move on to adding more layers. Let's next add, I'm basically just picking random numbers here, but let's add another layer, this one with kernel size 3 by 3. Can change the activation function. Let's see, can use 10H. You don't have to specify the input shape again because this is no longer the first layer. So it's going to automatically figure out how to connect these to one another. So you don't have to specify the input. Yeah, okay. So yeah, so you can basically just keep going, whatever architecture you have in mind. So remember that right now I'm not really thinking about like what is the right architecture for this particular data set. We are just basically trying to see how to implement CNNs. We are not worrying about the architecture, but it is very important to take your domain knowledge into account in deciding what architecture is useful for the particular application you're working with. And usually people try to see what has worked in the past. So the number of papers on deep learning architecture is getting bigger and bigger by day. So there are all these potential related work that if you're trying to figure out what the architecture is, you can go back and look at and see what usually works and basically take other kind of like domain knowledge that you have into account. So anyway, so we are not doing that here, but again, like once you have the architecture, the implementation is going to be similar to what we're doing here. So so far we have seen how to add the convolution layer. We can also similarly add a pooling layer. So the pool size, let's say it's 3 by 3. Again, you can, after convolution layers, if you want, you can have pooling layers. These are, again, decisions that you should make when designing your architecture. You can have dropout layers. So as you can see, this is amazingly modular. You basically just call cnn.add and add whatever layer you want to add to your architecture. So the dropout, I give as an argument to it the probability with which it should drop out units. And okay, so that's it for now. Let's just have these layers, right? So 2 convolution layers, 1 pooling layer. I added a dropout layer. Now, in the end, let's have a fully connected layer and then the output layer. So again, remember that for the fully connected layer, we use dense, but before that, we need to make sure that we flatten the, yeah. Right, so, but you can specify which layer it should be applied to, right? So remember that like with dropout, what you did was that you dropped a unit with probability P. So you can basically say that for each particular layer, you could potentially use a different P, right? So I'm adding the dropout to one particular layer. I'm not adding it to the entire network. You can do that too, but you might want to have, different dropout parameters for different layers. Previous one, yes. Okay, so, right, so let's first flatten, so the output so far. This is, again, you just add a flatten layer. So you need to do this before you add a fully connected layer, but for the fully connected layer, you use dense, right? So the arguments to dense, the first one is the number of outputs from that layer that you want. So, I don't know, let's have 100. And then you also need to specify the activation. So, and then at the end, I would like to have the output. So for the output layer, so the output layer should basically, in the output, you want to have one output per class, right? So we have 10 different classes, so we want to have 10 outputs. And we want to use, let's say, softmax to basically decide which one of them to output as the final prediction, given the input. Okay, so that's pretty much it, right? So I've specified the architecture. It's very easy to add more and more layers, and implement your own architecture. But once you have that, what you want to do is you want to compile this, right? You wanna call compile. So here, where you need to specify the loss function. There are a bunch of different loss functions you can choose. We're going to go with cross entropy. You also need to specify your optimization method, right? So what I'm going to do next is I'm going to train the model, right? So before I do that, I need to specify what my loss function is and how I'm going to optimize for it. So the first argument specifies the loss function. The second one specifies the optimizer. You could use stochastic gradient descent or whatever you want. Again, Keras has a bunch of different optimizers you can use. I'm going to use this one. And also metrics I want to have computed. Let's have accuracy. And that's it. Okay, so I've compiled the model. Now I want to fit a model. I want to basically train my model to get the parameters. I need to, before I fit the model, I need to specify some parameters of the optimizer. So batch size, I don't know, 80. To make things quick, we're going to assume we have just one epoch. And that's it. We can now fit the model. That is done simply by calling fit. So you give it the training data. You specify the batch size. So you specify the epochs, which I chose to be 1. This is a parameter that you don't have to worry about for now. And then you also give it the validation or test it. Okay, let's make sure we have everything. This should work. Okay. Now, so what you can see is that the model is starting to train. And it shouldn't take too long, given the parameters that we chose. But as the training is progressing, you can see how the loss changes. It is constantly going down. And then once the training is finished, all we will need to do is to just see what is the loss or accuracy on the training data. And that's pretty much it. Any questions? Yeah.
What do we need? You need different activation functions.
Sorry, could you repeat your question?
So first, when you make the first layers, you use RELU.
Right.
As an automation, and then you use hyperbolic activation function.
Right.
And so what I would like to know what do we earn by using different activation functions throughout the layer?
So again, remember that I'm basically choosing these parameters mindlessly here. I didn't have a particular intention for using a different activation function, but this is something you can do. And so again, remember that these activation functions have very different shapes, right? So they get activated very differently if you feed them the same number, right? So remember that this activation function is applied to a number, right? So if you give the same number to 10H, let's say, or ReLU, these are going to give you very different numbers, right? So they get activated differently. And the choice of what you want to do, again, depends on what has worked in the past, what you, given your knowledge about the input and the type of patterns you want the filter to pick up, what you think is going to work, and that kind of thing. So that is how you decide about the activation function. So these days, the activation function that is very widely used is ReLU, but by no means that means you should always use ReLU. Okay, so they have different properties. Like for instance, in terms of differentiability, they have different properties. So yeah, these are things that you have to worry about when you're actually working on an application, but at the moment, I'm basically just choosing them mindlessly. Okay, so the training is finished with accuracy 94%, which is not bad. And now what we are going to do is we are going to evaluate the model on the test data. Okay, so if you look at the second, so score is going to have two elements. The first one is the loss, the second one is accuracy. So again, the accuracy on the test is even better than the train, is 98. Okay, so that's it for the Keras tutorial. Let's now switch back to the old laptop and continue the lecture. All right. Okay, so let's wrap up the discussion about neural nets and convolutional neural nets. So again, remember that for regarding the last question that just came up, so there are a lot of different choices that you want to make. For instance, activation function is one of the choices you want to make. Yeah, actually, we pretty much covered this slide in answer to the previous question, which is nice. Okay, so let's see. These are some pros and cons of using neural nets that have already been extensively discussed, so I'm just going to skip them in the interest of time. So, so again, there are all these parameters that you need to pick when working with neural networks. You need to decide how many layers, how many hidden units in each, how many convolution layers, pooling layers when you're working with CNNs, the weight initialization, the type of regularization that you want to use and all that, right? So these are all choices that you need to make before you start implementing your model. But once you have the architecture, you can use these frameworks for auto-differentiation. We just looked at one, Keras, to implement your architecture. And you can, as always, use cross-validation to compare different models. Okay, so that was just a summary of neural nets. So the last thing I would like to cover before we finish this session is a quick comparison between artificial neural nets and kernels. So again, remember that so far we have talked about two main approaches for learning nonlinear models. The first one, the first nonlinear type of model that we talked about was the use of kernels. And the idea there was that you would start with linear methods. You would apply the kernel trick, which would basically allow you to solve a linear problem in a higher dimension, right? So what a kernel would do was to transform your features into a new set of features, right? And then you didn't have to do this transformation explicitly. What kernel trick allowed you to do was to do the inner product without actually explicitly specifying the transformation, right? So that was the idea. So by doing that transformation, you were left with a linear problem in a potentially higher dimension space, but still it was a linear problem, and you could you would have an optimization problem, a convex optimization problem to solve. So you could just go ahead and solve that convex optimization problem, get the global minimum, and you would be done with your training, right? So that was the high level idea behind kernels. So for neural networks, on the other hand, you explicitly specified a nonlinearity, right? So let's look at the type of functions that we can model with a single layer neural net, for instance. So what you did was, with neural nets, you explicitly added these nonlinearities. Here, for instance, we have the 10H activation function, and you basically fed a linear transformation of your features into this nonlinearity, and then take a linear combination of them, right? So this was what you pretty much did when using neural nets, right? So the first one basically was an implicit nonlinear model. It would allow you to implicitly specify nonlinear decision boundaries, whereas the second one, you basically make things explicit and you introduce this nonlinearity into your model. So what our goal now is to understand how these two nonlinear class of models relate to one another, and when you should prefer one to another. So there are, just to be clear, there are a number of different connections between these two class of models, but we are going to focus on a very simple one for now, and we are going to do that via the following example. So let's look at the type of functions that we are able to model using a one hidden layer neural network. So again, if X is your feature vector, the type of functions that you're going to be able to model, the class of functions that you will be able to model will all be of this form here, right? So an inner product of the feature vector with some coefficient. We take we apply the activation function to it, and then take the linear combination. So for instance, for the 10H one, remember 10H was of the following form, right? What we are doing here, assuming that X is one-dimensional, you're basically scaling and shifting this function and adding a bunch of them up to one another, right? So what this part is doing is that you're scaling the function, right? So again, think of this as a one-dimensional thing. So you have a coefficient, a one-dimensional coefficient times your one-dimensional feature. What that is going to do is that it is going to scale. So it could potentially make your function look like this or this, something like that. Right, so the first part does the scaling, and then the second one is, and also because we assume that there is, we are working with the feature vector that allows us to add allows us to shift. These could also get shifted, and then you would take a linear combination of all these, and that would make up your function. So, for instance, your function could look like something like this, right? So here, this is X, the one-dimensional feature. This is f of X. So you basically combine a bunch of shifted and scaled 10H functions, and when you add them up, you get a functional form. So that was so this is the class of functions that you can model using a single hidden layer neural network. So now let's look at kernels, and in particular, let's compare this class that we just talked about with the class of functions that you can model using kernels. Using 10H kernels, right? So if you remember, another name for the 10H kernel when we were discussing kernels was neural net kernels. And that was basically getting at this connection we are discussing now. So here, remember that the kernel trick was that you would, well, given a new feature vector, you would compute the inner product of the feature vector with the instances you've seen so far, then apply the 10H, right? So this would be the kernel evaluated at xi and x, and this was supposed to be the inner product of a transformed version of xi and transformed version of X. So this was basically the idea of using kernels. So right now we are using 10H kernels, and then with kernels, all you did was you learned the alpha i's, right? So you would apply the kernel, and then you would learn these coefficients. So if you think about it, so the class of functions that 10H kernel allows you to learn is exactly the class of functions that you can learn using a single layer neural net with the 10H activation, right? So if you basically just need to see the equivalency between theta I here and xi here, wi here and alpha I here, right? So is that clear? So these are basically the same class of functions. It doesn't mean that with the same input data, they're going to give you the same model. That is not what I'm saying. What I'm saying is that the class of models that a single layer neural network can potentially output is the same as the class of functions that applying 10H kernel can potentially give you. Is that clear? So again, I don't mean that given the same input training data, these two are going to give you the same model. But if you look at the space of all possible training data and specify what each of these models is going to give you as the output model, those two are going to be equivalent. So that is one way of thinking about the connection between kernel methods and neural nets. Okay, so there are, as I mentioned earlier, there are a lot of other connections that we are not going to cover in this course. But for instance, at a very high level, another known connection is that certain kernel methods can be thought of as the limit of a particular architecture of neural nets when you allow the number of hidden units to go to infinity. That kind of thing. So, yeah. So that's true if you want to do the training, and that is what I'm going to get to in a second. When you do training, you have many more free parameters in your neural net compared to the kernels. But basically for any neural net that you consider, if you assume that the data points that you've observed are exactly equal to this data that you've learned, right? You could potentially. What I want to say is that for any, okay, how do I say this without being confusing? So for the same training data, when training the neural net, you have many more free parameters compared to kernel methods, and you are not going to get the same model. Potentially with neural nets, you have much more freedom. You can model more complexities in your data. But again, I'm not claiming that they are going to give you the same model. All I'm saying is that the class of all models that each one of these can potentially output for some input training data, those two classes are the same. I'm not saying that for the same training data you are going to get the same model. Does that make sense? And if you want, we can continue this offline, and I can tell you a bit more how the equivalency is going to work. Okay, so that is actually an important point that I wanted to make anyway. So while these classes, the classes of function that these two methods allow you to model are equivalent, that by no means mean that they are the same. That training each one of them is a very different process. For instance, when you're optimizing alphas, working with kernels, you have a convex function, right? Because if you think of this as a function of alpha, the function is linear. Of course, if you think of it as a function of x, it's not linear, but that's not what we have to worry about. What we want to optimize for are alphas. And this is a linear function of alpha and can be very efficiently and exactly optimized. And that gives kernel methods a robustness that neural networks do not exhibit. On the other hand, if you are to train a neural net, as you mentioned, we have more free parameters. You can these are all trainable parameters, so you can train to find out what theta I should be and also what wi should be. But again, because of this nonlinearity that we've introduced here, the resulting function is non-convex, right? And it is not very easy to optimize for it. It is not easy to find the global optimum for the resulting optimization problem. Again, we talked about the fact that one can still apply techniques from convex optimization. One can still apply stochastic gradient descent. And in practice, this usually works well. You get a decent local minima, but again, there is no guarantee how far you are from the global optima. So in that sense, like, neural networks are much less robust compared to kernel methods. So that is one important distinction between the two. So another thing that I would like to emphasize is that given this different robustness properties, given the application, you might want to prefer one to another. So for instance, if the data is very noisy, probably kernel methods are going to be more, not probably, they are going to be more robust. Using kernel methods, it is less likely that your model is going to try to fit the noise, whereas using neural nets, it's likely that your model is going to try to model noise, right, which is not a good thing. So depending on the application, you might prefer one to another. What I would like to make sure everyone understands is that there is no strict preference. Like, you can't say neural networks are always better, right? So there are a lot of consequences for this modeling choices that we make for each one of them, and you want to be aware of all these consequences. So with that, we have another demo in which I'm going to try to make these points using examples. Let's see. Okay. So in this demo that we have here, we can choose one of the 4 different functions. Let's compile this again. Okay. Okay, now it's working. So you can basically choose different functions. We are going to get the sinusoid, but there are other functions you can play around with. Let's stick to this one. So what you can do is that you can train a neural network to fit this function, or you can use kernel methods. You can use the kernel trick to fit the data. So let's first do neural nets. So the number of samples, let's say it's 200. For now, I'm not gonna add, I'm gonna add a little bit of noise. Again, here you can choose between neural nets and SVM. Let's stick with neural nets. The activation, let's keep ReLU, the solver, the hidden layer. If you have one hidden layer, this is the best fit you get, not very good. So let's add more. Let's add another layer. All right, so as you can see, like neural nets can easily interpolate the data. So, and this is to be expected, right? Given the universal approximation theorem, you expect this to happen. But with more and more hidden units, you should get a better fit. Now let's try SVM. Again, the kernel, you can use RBF or Laplacian. I'm going to keep these other parameters. So here is the fit you get with SVM. If you play around with the parameters, you can see how it affects your output model. Now let's, so it looks like when we have no noise, neural networks are doing better. But again, like it's hard to compare because the parameter setting is done differently for them. It is hard to compare them in a sense. They're apples and oranges, but let's add more noise and see. So I guess it's first to say that for now without noise, neural nets are performing pretty well. But again, I don't wanna make a general statement. So let's add a lot more noise. All right, so again, the function itself is the sinusoid. What we're doing is we are adding Gaussian noise to the model. So as you can see, now the neural nets is basically interpolating the noise, right? It is trying to model the noise, which is not good. Whereas Oops, this was SVM, but with no regularization. Let's now do neural nets with okay. So this is the type of thing we get. Let's do SVM again. So neural nets try to interpolate the noise. Let me add to the regularization here. Okay, by changing the bandwidth of the kernel, you get a much better fit, right? So instead of trying to model noise, the kernel methods can easily find a pretty decent approximation of the function, right? Whereas neural nets would attempt to model noise or pick up information in the noise. So that was one point I wanted to make. What else? So yeah, I guess that's mostly it. You can again play around with this more to get a better sense of what's going on as you change the parameters of each model. But here is like an overview of kernel methods versus artificial neural nets. So again, with kernel methods, the nice thing about them is that they result in a convex optimization problem. You won't have issues with local minima. As we just saw, they are more robust against noise. And the other nice thing about them is that as the number of training instances increase, your model becomes more and more complex, right? So remember that. So you, for a new instance, you would take the inner product with previously seen instances. So as the number of instances in the training data increases, your model becomes more and more complex, which is good, right? So if you don't have enough data, you don't want to attempt learning a very complicated model, right? On the other hand, if you have enough data, it is probably okay to try to learn more and more complicated models. But again, this is both an advantage and a disadvantage, because on the other hand, like if the number of training instances is too big, then this becomes hard to manage, right? You have to, you basically have to keep track of all the previous training instances. So on the other hand, the disadvantages of kernels is that the main disadvantage is again the fact that the model grows with the size of data. And another one is that it is hard to model nested nonlinearities with kernels. This was something that was easy to model by neural nets, but not so much when you use kernels. So on the other hand, if you look at artificial neural nets, they give you a very flexible class of models. There are a lot of parameters. There are a lot of free parameters that you can train. You can have multiple layers of nonlinearity, and that would allow you to have multiple levels of abstraction. For instance, in the image recognition example that we talked about, the first layers could pick up generic information about image patches, and as you went deeper and deeper, your filters could pick up more specialized information about the image patch, right? So that is the nice thing about artificial neural networks in general. They allow you to have multiple levels of abstraction. But the fact that we have so many free parameters and so many choices that we have to make about the architecture of the network makes them a bit hard to work with. You really need to have a lot of domain knowledge to know what architecture to use, what works, what doesn't work. There are a lot of tricks that one has to be skilled in. And as we saw in the demo, we have robustness issues, right? So for the same architecture, if you train it multiple times, every time you are going to end up with a different model. And that is not very good, especially in applications when you really need robustness, right? So these are, and the other thing is that, like, if you have if you have clean data, neural nets are going to be very good at picking up patterns, but if your data itself is problematic, let's say you have data points that are mistakenly labeled, your neural nets is going to learn that and is going to repeat those mistakes. That is another issue with neural nets. So again, neural nets are definitely more complicated to work with, but again, given the application, one has to discuss which one is a more appropriate choice. So here is the overview slide that we've been populating over time in this class. So again, supervised learning can be thought of in terms of the following aspects. You need to first decide what representation you should use for your data, what model you want to use, how you want to train them, how you want to do the training and fit a model, and how you want to evaluate it, right? And we have so far seen many different approaches to each one of these. In particular, in terms of representation, with neural nets, we learned about yet another nonlinear way of representing the data. For the loss function, I don't think we added a new loss function, but we added new regularization methods, including dropout and early stopping. And I guess that's it. So with that, we are going to conclude the discussion on neural nets, but also the discussion on supervised learning in general. Next session, Professor Krause is going to start a series of lecture on unsupervised learning, where the idea is that instead of having a labeled training data, you are going to have unlabeled training data. And a typical example of unsupervised learning is clustering, where you basically want to divide your input into groups. So you're going to learn more about that next session. Thank you.